All right, before we can really talk about intermolecular forces, we have to actually go back and look at the basics of bonding for a moment to make sure that we have a couple of things clear, because that's going to lay the background to all of the forces that attract things together. First, when we have a difference in electronegativity, so-called delta En of greater than 1.9, we're looking at an ionic bond. So if we want to picture the electrons between the two atoms, essentially it looks a little bit like this. One has taken them and moved apart. This is just a simplification, not geometrically true, but a simplification. One has taken the shared electrons and left. The other lost something. So we have, as a result, formal ionic charges, +1, -1, sometimes more charge than that. But when we talk about attraction to other molecules, the magnitude of charge is a big deal. Full charges, ionic compounds, ionic atoms, or ionic groups, have the largest magnitude of charge. So that's going to be a big part of what we see very shortly. If, on the other hand, we're talking about a case where we're not above that 1.9 threshold, the difference in electronegativity, but we're somewhere in the middle between about 0.5 and 1.9, or some books say between 0.4 and 1.9, we're talking about a shared pair of electrons. It is a covalent bond, but the sharing is very lopsided. So we're looking at something where there's still not really equal sharing. Geometrically, you could sort of picture that as one atom having a little bit closer and one atom being a little further from them. It's not strictly geometrically true, but it's an easy way to visualize it. One has a better grip, more electronegative, the electrons are a little closer. The other has a weaker grip, less electronegative, the electrons are a little further. As a result, they're not ions. They don't have full +1, -1 charges, but they're getting there. They're already polarized, as we use the term. And to denote that, we use the lowercase Greek delta to indicate that the charge is a partial one. If you're in differential equations, it's the same thing you use for partial derivatives, the lowercase Greek d instead of a regular Roman d. That way we can denote that there's charge there, but it's not up to the level of ionic. When we talk about quantitative, this is a little difficult for us, but at least we know that magnitude is less than 1. So when we talk about, putting things in an order of magnitude of charge, this will be lower than the ions were in the previous example. If we have a pair of electrons that are shared equally, roughly, somewhere between an electronegativity of 0.0 difference, meaning two equal atoms, usually, or up to about 0.5, usually 0.4 is the threshold that's used, the sharing is roughly equal, so that there's no real constant and consistent buildup of charge on either atom. Here's a case where we have very tiny magnitudes of charge, but only because we have fluctuation of where those electrons are at any given point. Remember, they're not static things. They're always in motion. So at any given point, they're going back and forth, as you see here, between the two atoms involved. And as a result, there's always a little trace of charge building up on those two atoms. But it doesn't stay that way. It's a fluctuating charge, and it's very, very tiny. We'll sometimes denote that with two lowercase Greek deltas, two lowercase d's here, to say that it's very, very, very tiny amount of charge. But tiny is not 0, and we can work with something that's not 0. Zero charge ever would be something where attractive forces electronically wouldn't exist. We do have some weak ones that are going to require us to delve into this tiny fluctuating charge that you see here. Okay, the basic thing we need to think about from physics terms is Coulomb's law. Attractive force or repulsive force, if the charges are identical, is equal to a constant k times the magnitude of each charge, q1 and q2 as an absolute value, over the square of the distance between them. Now that, in our terms, is going a little bit more into the physics mathematics than we care to do right this moment. But what we really need to think about is the attraction that we're going to deal with, if we're talking about opposite charges, is proportional to the magnitude of the first charge, the magnitude of the second charge, and inversely proportional to the square of the distance between them. Now, notice what we talked about before. Ions, larger magnitude of charge. So we see those here. Aluminum, magnesium, sodium, bigger charges. 1, 2, 3 cations, or below that, nitrogen, oxygen, fluorine, 1, 2, 3 anions. Polar covalent bonds, we get partial charges, but we still have a charge. Now the electronegativity I have below the H and the O here, so you can see what they are, a difference of 1.4. So a little bit of positive charge on the hydrogen, a little bit of negative charge on the oxygen, and we're only considering one bond at a time here, so the other one we can ignore. And motion going back and forth between two atoms is at the very bottom of our magnitude of charge. It's very transient, it's very small, but it's not zero. If it were zero, that whole equation we had earlier, 0 times anything is 0. We'd have no attractive force. But we do still have some, even in purely neutral compounds. It's very small per bond. So we're going to deal with that in a moment. Okay, so now we can actually talk about what holds molecules together, intermolecular forces. The first and the strongest of them is what happens when we bring an ion near something that has a dipole moment, or polar covalent bonds. That is to bring something with a full charge, or more than one full charge, +1, +2, -1, -2, near something with partial charges from a polar covalent bond. So polar covalent bonds, we would call that a dipole. In a atom or a group of atoms state, it's an ion with a full charge. So here's what that looks like. If we look at, for instance, sodium chloride in its interactions with water, the first thing that water does is help to actually separate the ions. So we're just going to ignore the chlorine here for a moment and assume that it got separated out. Well, we have a plus charge on the sodium, we have a very small partial minus charge on the oxygen, so we're going to have an attraction based on those two magnitudes of charges, and the closer they get, the better that attraction is going to be. So sometimes you'll see this drawn with a dotted line like so. Some books like that, some don't. As long as you're very clear it's not a bond. Okay, this is an attraction because they're next to each other, not a formal bonding arrangement. But the point is opposite charges do attract. There are opposite charges here, so there is some attraction. All right, so this one is a big one. Now, why is this a big one? Because aside from just the usefulness of understanding it, it's also a big one because it explains why it is ionic compounds typically dissolve very well in water. Water happens to have a permanent dipole moment. It has a very polarized oxygen, so it's going to be attracted to anything that's cationic. So it helps to dissolve all of the salts, for instance, that are circulating in your body right now. So calcium, magnesium, sodium, and potassium are the 4 ions responsible for a lot of regulation of your bodily systems. Well, guess what? They all better dissolve in water pretty well, since that's most of what you're made of. If they don't, we'd have a big problem. Okay, so what if we don't have formal charges? Well, if we have something that has a polar covalent bond, I've used formaldehyde here as an example, because it only has one, so we don't have to worry about multiple directions. We still have a buildup of partial charge. Sometimes we'll draw a dipole moment on it with arrows like this, and that just indicates the direction of a force, so that the electroforce, the polarization of the molecule goes from the positive end. So you can see the arrow has kind of a cation positive at the end of it, points towards the negatively charged end of the bond. So what we're going to see, very much like before, is opposite charges are going to attract. That means that if we move these around a little bit, we're going to see the oxygen on one attracted to the carbon on the other, and so on and so on and so on. And as a result, what we have is something that behaves much more coherently than if it were an isolated molecule in the gas phase. We'll talk more about that because it becomes a really big deal with water. A separate type of dipole-dipole interaction, it still technically is one, that's why I gave it the same number, is hydrogen bonding. Now, obviously this limits us to at least one atom of the set has to be a hydrogen. In fact, it limits us pretty severely, but it works like so. We have an element with a lone pair of electrons bonded to a hydrogen. That is a very polar bond. We showed that before with water. However, in this case, we're going to take advantage of the hydrogen as well, that it interacts with the other of what I have labeled Z here on the next molecule down, and that can enable networks of hydrogen bonds to happen. In water, that becomes a huge deal. But there's a big strict limitation here, is that hydrogen bonding only happens if the other atom is either nitrogen, oxygen, or fluorine, nowhere else. So we only have 3 elements attached to hydrogen that can give us hydrogen bonding. Now, if you're looking at the periodic table, you're going to think, well, that's kind of a limited set. Why do we bother to even talk about this junk? Well, first of all, there's water, HOH. That's clearly a big one that we're going to have to worry about. But we also have things like amino acids. Now, I've drawn a neutral version of an amino acid here. Notice what you see. You have 2 oxygens, both with lone pairs. You have a hydrogen on the oxygen on the right. You have a nitrogen with a lone pair, and you have hydrogens on that nitrogen. So you have 3 hydrogens that could be involved in hydrogen bonding. You have 3 atoms with lone pairs of electrons that could be involved in the other side of hydrogen bonding, what we call an acceptor for hydrogen bond, or a donor of a hydrogen bond. The hydrogens that could be involved are circled here. Now, in a more complex case where we're talking about proteins, large chains of amino acids, one of the hydrogens on the nitrogen and the OH group on the right are gone. They're actually used to form other connections. But all those other pieces, what you see here with blue dots, are still present. We have hydrogen bond acceptance from the oxygen at the top. We have hydrogen bond acceptance potentially from the nitrogen at the bottom. And we have hydrogen bond donation from the bottom hydrogen, which would still be there, even though the other one that was originally present is gone. So we have 3 possible hydrogen bond interactions per amino acid. And remember, each protein that you have is sometimes dozens, sometimes even hundreds of amino acids long. So there's a lot of this going on in even one single protein. Okay. In the simple case, we can look at it in terms of properties, and this is the way your book will approach it, is we start from something on the far left, methane, CH4, that has no hydrogen bonding. The other 3 examples here all have it, right? Oxygen, nitrogen, and fluorine. We're going across the periodic table. We can look at this in property terms by looking at, for instance, the boiling points. For methane, CH4, minus 161. What does that tell you? It has virtually no interactions whatsoever. There's no attraction of any magnitude between individual molecules there. It becomes a gas so low that it's not even worth talking about in a practical sense for most of the cases. Look at what happens when we go to something like nitrogen. Well, now we're very similar structure-wise. It's still basically a tetrahedron with one of the groups replaced with a lone pair, so it's pyramidal. Same rough shape, but it raises the boiling point by 130 degrees. Okay, that's a huge change just by introducing one atom that can actually act in hydrogen bond terms. It allows the nitrogen to act to accept hydrogen bonds, and potentially all 3 of the hydrogens there to act as donors of hydrogen bonds. If we move one step further over, we're now up to another 130 degree increase in boiling point with water, because we now have 2 different lone pairs on the oxygen potentially acting as hydrogen bond acceptors, and 2 different hydrogens potentially acting as hydrogen bond donors. So then what happens at the end? We end up with HF. We've got now a 3rd lone pair of electrons, but we're now dropped back down significantly in boiling point. What is that? Why does that happen? Well, think about it. Oxygen can donate to and get to. HF can't do that. It can really only form what would be approximately linear geometries of hydrogen bonding, whereas ammonia to some extent, water to a very large extent, can form extensive 3-dimensional networks, and that makes a huge difference. But let's take a look at what happens when we replace one of those groups, just to see what happens when there's only one hydrogen available. I'm going to do this only for nitrogen and oxygen. It makes things a little simpler. So we're going to replace one of the hydrogens on ammonia, NH3, and one of the hydrogens on water with a carbon group that basically can't hydrogen bond. Right? This is common substitution in chemistry later on. Look what happens. For ammonia, the boiling point actually goes up from minus 33 to, with this methyl group, minus 6. So that caused an increase, telling us that maybe networking wasn't such a big deal there as we might have thought. But water, it drops. So we replace one of water's hydrogens with a carbon, and its boiling point drops by 35 degrees, from 100 for water to 65 degrees C. The compound on the right is methanol, methyl alcohol. So networking there has to have been a big deal, because otherwise we'd expect this to go up in the way that the nitrogen one did. This is just one piece of how we can account for what happens later on. Water, as you can see what I've drawn here, forms very extensive 3-dimensional networks. I'll give you a link at the end of this for a model of what water shape looks like in the liquid and solid phases. We'll talk more about that in the next lecture, but the point is, it has hydrogen bonding going all over the place, and as a result, it behaves as if it's a very, very large molecule, meaning it's coherent, it's liquid, rather than a gas at room temperature and pressure, or at most conditions on this planet, it's a liquid. Vaguely helpful if you like being alive. And disrupting all of that's going to be very difficult. Remember, to get something to go to the gas phase, you have to break all of its attractions. So that's why the boiling point for water is so high, because you're not talking about just breaking 2. You're talking about breaking a lot of attractions here to get water molecules to leave each other. They like each other a lot. The next one at first is a little bit difficult to understand, so I've brought in a guest lecturer to help explain it.
Hey, I know you don't smoke weed. I know this. But I'm gonna get you high today. 'Cause it's Friday, you ain't got no job, and you ain't got shit to do.
Molecular equivalent of smoky there. And that is what happens when we have a molecule that has a dipole, the bad influence, if you will, versus one that doesn't. Now, oxygen on the right here, O2 gas, is a neutral covalent molecule. Obviously, they're the same atoms, so there's no difference in electronegativity, so there's no full charge there. We have that fluctuating charge that we saw before, but that wouldn't really help us in attracting to something that has a set charge. Well, here's what happens. You have a bad influence, a polarizing influence, and it induces that fluctuation to basically stay on one side a little longer. All right, so instead of the charges on the oxygen going back and forth at this, a very high rate, this interaction with the dipole of water actually stabilizes it a little bit and helps attract it to water itself. Now, I used the example before of this being a big deal, not because it's just interesting chemically, but because it's biologically relevant of all the salts dissolving in water. Well, guess what? You're looking at why aquatic life can breathe. Oxygen, to a small extent, relatively small extent, but not zero again, does dissolve in water. And so aquatic life relies on the fact that water has a very small, but not zero, attraction to oxygen gas. So fish breathe in through gills rather than through lungs. They don't take in gaseous oxygen. They take in solvated oxygen and separate it from the water, and then their respiratory system from that point, or their circulatory system from that point, is very similar to ours. They process the oxygen very similarly, but how they take it in is different. We wish we could do that, but it's not quite so simple. It's a completely different system than the way our body processes the oxygen. You have lungs, they're designed for actually processing gas. Fish don't have that in the same manner. That's why if you take a fish out of water, if you've ever seen that, they seem to be gasping even though they're in the middle of oxygen. They just don't have the gear to process it the way that we do. Same thing happens to you if we hold you underwater. You don't have the gear to process that, so eventually you'll be gasping too. And the bubbles will stop, and that'll be the end of your suffering through chemistry. Okay, so the last one is the one that I said was a little bit difficult to understand, and that is what happens when we don't have polar molecules at all. We have no set polar bonds in a molecule. Well, we still have those fluctuating charges, but in a simple molecule, something like methane on the left here, what we put up before, that's not much. Doesn't count for much. It boils at a minus 161 degrees C. That essentially has such a small attraction that it's almost not worth talking about. But a similar compound on down the line from that, same family of molecules, so same bonds, carbon to carbon ones, no electronegativity difference, no polarization. Carbon to hydrogen ones, same as the type that are on the left here with methane. Instead of having 4 bonds, you now have 19 of them, all fluctuating charges, all interacting with other molecules. And so what happens as you stack this up is that you start to build up enough of an attraction of those little small things to actually do the job. Now, there's a famous joke that you can make about this. Some textbooks will do it, and I have this dream of doing it myself one day, is that when you go to make the final payment on your house or your car or whatever, you come in with, several $1,000s in pennies. It's annoying, all right? It's frustrating. But the point is this. By themselves, those pennies are worthless. 3 or 4 of them together, as you see for methane, not worth much. But you start stacking them up to where you see in hexane, and they start to be enough to buy something with, enough to actually keep things coherent, enough to make something a liquid, and eventually enough to make something a solid. It takes a few more atoms down the line to manage that, but the point is, you still don't have any big charges, you just have a whole bunch of really tiny ones that you're adding up. So larger molecules tend to be solids, meaning larger number of atoms tend to be solids beyond a certain point because you have so many small interactions. Not because any one big thing is holding them together, but lots of little ones are doing it.